Good day, Calc 2. I'm going to talk to you a little bit today about some of the problems from section 6.5, exponential growth and decay. So let's suppose we have a population, say of lemmings, in a controlled environment, meaning no predators and plenty of food and resources. This population of lemmings will grow at a rate proportional to the amount of lemmings present. Now what does this mean? Well, it means if you, say, have a small number of lemmings, like 20, you might grow 4 lemmings per hour or per day or whatever. And if you have 200 lemmings, you might grow at 40 lemmings per hour. So the rate of growth is proportional or dependent upon directly the amount of items you have. Certainly, if there's more in the population, the number that grow per unit time will be larger. Let's suppose that population is given by the function y of t, where y is the population of t is time. Saying the rate at which the population grows is proportional to the amount present is modeled by the following differential equation. dy dt equals k times y, where k is a constant. And in this case, k is greater than 0. Since the population is growing, k is greater than 0, this is called the law of natural growth. For example, if we say that a population is growing at 2% per year, and if this is the population after t years, then dy dt is the rate of change of the population, or how many you're growing by every year. And you say that's going to be 2% of the current population, right? So this right here, and we don't normally write that of t there, this right here represents a differential equation. This is called a differential equation, and this is the example that we have. We have rate of growth equals 20%. I use 20%, not 2, right there. So that would be 2%, okay? So that's 2% per year. Now, suppose you have a radioactive substance, and it decays with respect to time, because that's what radioactive substances do. The amount that decays at any given time is proportional to the amount present. If you have 1,000 grams of this substance, and you lose 10% every hour, then 10% of 1,000 is 100 grams. While if you only have 1 gram of this substance and still lose 10% per hour, it's 0.1 grams. So again, the rate of change is proportional to the amount present. So if y of t is the amount present at time t, then the situation can be modeled again by the equation dy dt equals ky, where k is constant. In this case, k is less than 0. If k is less than 0, this is called the law of natural decay. In either case, this differentiation is solved by a function that is a constant times itself. Solved by a function whose derivative, is a constant times itself. What function do you know satisfies the property that it is a derivative times itself, a constant times itself? That has to involve our friend e. So I claim the only solution to the differential equation dy dt equals k times y is y equals c e to the kt. And let me give you a proof. dy dt equals k times y. I'm going to multiply both sides of this by dt. Okay? Then I'm going to divide both sides of that by y. The technique I'm using is called separation of variables. Now, I'm going to integrate each side. What is this integral of this side? Well, that's 1 over y dy. And this is k times dt. The integral of 1 over y is ln absolute value of y. And the integral of k times dt, since k is a constant, is k times t plus a constant I'll call c1. Now I could have put a constant on each side, but since this is any arbitrary constant, I'm just going to put it here. Now, I would like you to undo this equation. Remember, log of y equals something, is the same as writing y equals e times the kt plus c1. And I can divide that up this way, because if I add these two exponents, I get that. Now, this, since we're dealing with a population, populations tend to be positive, so I'm going to get rid of the absolute value sign. And if I notice e to the c1 is just a constant, so I'm going to let that constant be c, and here is my equation. So if I can set up a problem using this differential equation, this is my solution. That's the whole point of this theorem. So in particular, if time is 0, then the equation says y of 0 equals c to the ek times 0, or c to the e times 0, or c. So we have the following theorem. The only solution to the differential equation dy dt equals kx are the exponential functions y of t equals y to the 0 e to the kt. This right here is so useful that we're going to do some application problems that are stressed by this. So let's look at this. A bacteria grows with a constant rate relative growth rate. After 2 hours, there are 600 bacteria, and after 8 hours, the count is 7,500. What is the initial population? Find an expression for the population after t hours. Find the number of cells after 5 hours, and find the rate of growth after 5 hours. When will the population reach 200,000? Now remember, we have proved this theorem above. If I can justify to you that this situation is modeled by that differential equation, then I can just use this. So let's think about this. A bacteria grows at a constant relative growth rate. What does that mean? Well, let's let b of t equals the population of the bacteria at time t. So db dt is got a relative growth rate. That means that it's a constant times the amount present. So this sentence right here tells me that this is represented by this growth rate is represented by this differential equation. By our theorem, that means b of t is equal to k is equal to b of 0 times e to the kt. So all I have to do to solve this problem is find that initial value and that constant. Now, I know I don't really want to write down this b of 0 all the time, so I'm just going to write it like this, with a little subscript there. And what do I know? Well, I know after 2 hours that you have 600 bacteria, which gives you b e to the k times 2, just replacing t for 2. And after 8 hours, you have 75,000 for your bacteria. Now look at these two equations. I'm going to write them over here. 600 equals b e to the 2k, and 7,500 equals b e to the 8k. How can we solve these? Well, what I would do is something along this line. I might take this second equation here, 75,000 b e to the 8k, and isolate for b. Okay, so there I've done that. Now I'm going to substitute this into the first equation. So instead of 600b e to the 2k, I'm going to put in 75,000 over e to the 8k, and multiply that by e to the 2k. That gives me 75,000 e to the 6k. I'm just subtracting exponents there. You have to remember your law of exponents. I'm going to do a little cross multiplication here. And we have that. Now I'm going to take the logarithm of both sides. And I'm going to divide by 6. This value right here is my value of k, right there. That's my number. Now, to find b of 0, I would substitute that into this and find b of 0. So this is what I have here. So b of 0, let me put those zeros there. I forgot to put them on these. B of 0 equals 75,000 over e to the 8k. When you figure out what k is, you can put it in there. So I'm going to figure out what k is right now. I'm going to go over to my calculator. 1/6 times ln 750 divided by 6 is 0.804. So k is approximately 0.8047. So this is 75,000 divided by e times 8 times 0.8047. If I do that, I get that this is just about 120 if I round to my initial population. So that gives me the answer really to the first one, which is what is the initial population? The initial population is about 120. An expression for the population after t hours would be b of t equals 120 e to the k was 0.8047 was what I used, t. So now, find the number of cells after 5 hours. Let's just plug in 5 for t. If I do that, I get approximately 6,708. Find the rate of growth after 5 hours. The rate of growth after 5 hours is given by this. d dt equals k times y, right? So k here is 0.8047. So that's, well, not y, b. So that's my equation. Now, after 5 hours, what is the population after 5 hours? Well, the population after 5 hours, I just figured out, is 6,708. So this gives me a rate of growth of approximately that times 0.8047. So that ends up to be about 5,398 or so bacteria per hour. Now, when will the population equal 200,000? What we want is we want to figure out this. Now you can solve this problem using logarithms. You can solve it using your calculator. I'm going to divide both sides by 120. And I'm going to take the natural log of both sides. And t equals 1 over 0.8047 times the natural log of 200,000 over 120. Now we'll do that calculation. That's approximately 9.2 hours for it to reach that population. So fast-growing rate of bacteria population. The key to this was the idea that it grows at a constant relative growth rate, which means that the rate of change is proportional to the amount present. Let's do a half-life problem. Maybe, we talked about laws of exponential decay also. So here's a half-life problem. The half-life of cesium 137 is 30 years. Suppose we have a 100 milligram sample. Find that the mass that remains after t years. Well, in this case, the population, or the amount, is equal to the initial population times e to the kt. Because again, this is a half-life or radioactive decay problem. We know that that satisfies the law of natural decay. So I'm going to start with 100, and I want to know how much there is later. Well, I know the half-life is 30 years. So that means when t is 30, we're only going to have half of our initial 100 milligram amount, which is 50, available. So I know 50 has to equal 100 e to the k times 30. Now if I divide both sides by 100, I get 1/2 equals e 30 times k. Now what? Natural log of 1/2 equals 30 times k. 1/30 ln 1/2 equals k. If I do this, this ends up to be approximately minus 0.023. So here's my equation. P of t equals 100 e to the minus 0.023 t. Okay? So that's my population. That is my mass that remains after t years. So how much of the sample will remain after 100 years? Well, after 100 years, I'll draw a little line here. I'm going to plug in 100 for t, and we'll have this. So again, if I do that on my calculator, 100 e to the minus 0.023 times 100 equals about 10, or 10.025 milligrams to be exact. How long will it take for 1 milligram to be left? Well, in that case, I'm not replacing for t, but I'm replacing for p. I would solve this equation. So this is a nice little exponential equation to solve. Take the natural log of each side. So t is 1 divided by minus 0.023 times ln 1 divided by 100. And that's going to equal about, okay, so your time, how long, is about 200 years, 200.22 years for you to solve that equation. So these problems, you'll notice, really are very similar to problems you might have done in a pre-calculus class. Just kind of reminding ourselves about those laws of exponents and using this law of natural growth or natural decay right here. What are some other examples we can look at? Well, we can look at something called Newton's law of cooling. When I come back to see you next week, we might pop something in the microwave. If we pop it in the microwave and we leave it in there a long time, it's going to be very, very hot. Imagine I put a cup of coffee in the microwave and it ends up being super, super hot. So I take it out and I lay it on the counter, and I don't want to drink it right away. What's going to happen? It's going to start cooling. Now, it will cool faster, we know, if we put it in the refrigerator, right? Or if we put it outside in the snow. And that's because Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding. If T of t is the temperature of the object at time t, and T sub s is the temperature of surrounding, then we can write down this differential equation. dt equals k times t minus T sub s. Now, if you let y of t equals d of d equal T of t minus T of s, since T of s is a constant, this tells you that dy dt equals dt dt minus 0. So I can replace in this equation dd dt with dy dt. And this is a constant k, and this we've defined to be y. So what do we have again? We have our natural growth or natural decay equation. In this case, this is a natural decay equation. So this equation can be rewritten as this, and it can be solved as this function right here. Now, you have to remember what y and t are when you do this problem. So here's an example. The thermometer is taken from a room where the temperature is 20 degrees Celsius to the outdoors where it's 5 degrees Celsius. After 1 minute, the thermometer reads 12 degrees Celsius. What will the reading be after 1 more minute? Okay. When will the thermometer read 6 degrees? So here's what we have. Let's let T be the temperature of the thermometer at time t. And the temperature of the surroundings, they said, was 5 degrees. And we know that the initial temperature is 20, and the temperature after 1 minute is 12. That's just organizing the information in the problem. Now, if I let y of t equals t of t minus t of s, that's going to be t of t minus 50. And I know, because we just did this argument, that dy of t equals k times y. So I know that this is solved by the equation y equals c times e to the kt, where c is my initial amount. Well, my initial amount is what? Now remember, y is not the temperature. Y is the difference between the temperature and the surroundings. So the initial amount, y sub 0, equals t sub 0 minus t sub s. But t sub 0 is 20, and t sub s is 5, so that initial amount is 15. Now we need to find k. To find k, we're going to use the idea that y of 1 equals t of 1 minus the temperature of the surroundings. Temperature after 1 minute was 12. Temperature surrounding is 5. So y of 1 is 7. So I could say 7 equals 15 e to the k times 1. Or 7 equals 15 e to the k. Or 7/15 equals e to the k, which you can rewrite as ln 7/15 equals k. So my final equation for y is y of t equals 15 e to the, let's figure out what ln 7/15 is. It's about minus 0.762. Okay. All right? So there we have it. Now, when will the thermometer, what will the reading be after 1 more minute? Since we knew after 1 minute the reading of temperature was 12, after 2 minutes, this will give me this. So 15 times e to negative 0.762 times 2, just doing that on my calculator, I get that this is approximately 3.27. Now remember, that doesn't say you're 3.27 degrees. That says that the temperature after 2 minutes minus the temperature of the surrounding is 3.27 degrees. We know that the temperature of the surrounding is 5 degrees, so this would tell me that the temperature after 2 minutes would be about 8.27 degrees. Okay, so that's kind of a nice way to do this problem. That's not, we can use this little substitution to help us do what's called Newton's law of cooling. There's also Newton's law of heating, which says if you take a cold object and you put it out in the environment is warmer, it will warm up towards the equilibrium temperature. But it's the same exact differential equation, the same exact equation as this problem. Let's finish with one more example called continuous compounding interest. The formula for the future value of account where you invest $P at a yearly interest rate R, which is compounded n times per year, is given by this. Now, to give you an example, let's suppose you invest $10,000 at 6% interest compounded quarterly. That means you're going to get interest 4 times a year. You're not going to get all your 6%, however, every 3 months. 4 times a year is every 3 months. You're only going to get 0.6% divided by, or 6% divided by 4 every 3 months. And you're going to do that for 10 years. So you're going to do that 4 times a year every 10 years. If you use this formula, just doing the arithmetic yourself, you end up with $18,140.18. So, that's how much you will have after 10 years. Now, if I change this 4 to a 12, how does that change this? So this was quarterly. If I change this to a 12, I just go back to my calculator and I do that, but instead of giving you interest every quarter, I'm giving you interest every month. This goes up to $18,193.97. Now that's more, but not a huge amount more. Okay, I went up by, about $53. Not that that's anything to do here. What if I did this daily? I gave you interest every day, so instead of giving you the 6% per year, I gave interest every day, so I made this 365 and this 365, and I redo that problem. So I'll go back to my calculator and redo that problem. That adds up to be $18,220.29. So that, you'll notice, I went up, but I only went up about $27, not very much. So the idea here is as I increase this amount of times I'm giving you interest per year, this number seems to be approaching a limit. So we call that asymptotic behavior. And what is the limiting value? Well, let's do a little mathematics. So I'm going to let the limit as n goes to infinity of p times 1 plus r over n and t. That's my future value. Now I'm just going to rewrite this as 1 plus r over n to the n over r times rt. Notice if you multiply these, you get nt, exactly the same thing that you get there. Now I'm going to let m equals n over r. And as n goes to infinity, m goes to infinity, because your interest rate is constant. So I'm going to write this like this. Now, you should know that this limit right here is the number e. This formula, a equals p e to the rt, is the future value of an amount p invested now at r% for t years. This is called continuous compounding interest. We sometimes use the word PERT, like PERT shampoo, to remember this. So if $5,000 is invested, so 5,000 is my P, at 8% interest compounded continuously, how much will be in the account after 5 years? Well, $5,000 e to the 0.08 times t, which is 5. So let's figure that out. 5,000 e to the 0.08 times 5 is going to give me $7,459.12. So that is what is known as continuous compounding interest. And again, the amount of interest you earn is proportional to the amount present. So this looks very much like that law for exponential growth. I hope you find this lesson helpful in doing some of your homework problems. Feel free to contact me through WebAssign or via email if you have questions. Thank you.